Heating effect of an electric current. Let's start with an experiment. We have a power supply, that's a DC power supply, a thin metal wire, and an ammeter to measure current flow. We switch on the power supply and increase the current flow. Observe that at near 1.9 amperes, the thin wire becomes red hot. And so it's a matter of common experience today that whenever a large amount of current flows through a conductor, the conductor dissipates heat. This is called the heating effect of current. When a battery is connected across a conductor, a potential difference across the conductor sets up an electric field around it. Due to this, the electrons of the conductor get accelerated in the direction opposite to the direction of electric field. Large numbers of electrons start moving towards the positive end of the conductor under the influence of this electric field. On their way, they collide with vibrating atoms and ions of the conductor. They transfer their kinetic energy gained from the chemical energy of the cell. Due to this transfer of energy, kinetic energy of vibration of atoms increases, which in turn increases the temperature of the conductor. Thus, when current flows through a conductor, heat is produced. To investigate the factors affecting the heating effect of an electric current, in 1841, James Prescott Joule found that when current I is made to flow through a passive or ohmic resistor, the heat developed is directly proportional to the square of the electric current, resistance of the conductor, and the time for which the current flows. This equation can be written as H is proportional to I squared, RT. This statement is known as Joule's law of heating. Joule's law of heating by electric current can be verified in a lab using a Joule's calorimeter. The Joule's calorimeter consists of a nickel-plated copper vessel with a stirrer. The nickel-plated vessel is in a teakwood vessel. The outer vessel has a bakelite top with the provision for the thermometer. There are terminals present on the bakelite top to which a resistor is fixed. Let's see how to arrive at the Joule's law. Joule filled 2/3 of the calorimeter with m grams of water. He placed a resistor R inside the water. The calorimeter was connected to an ammeter and a rheostat. He noted the initial temperature of water, θ1, and then passed the current I through the resistor for a known interval of time, say 15 minutes. Due to the flow of current, the temperature increased to θ2. He calculated H1, the heat gained by the calorimeter and water. He repeated the experiment for different values of current by adjusting the position of the slider of the rheostat and calculated the corresponding quantities of heat produced. He found that H1 by I1 squared is equal to H2 by I2 squared, which is equal to H3 by I3 squared. This means that H by I squared is equal to a constant, or H is proportional to I squared. He then repeated the same experiment by passing the same amount of current through different coils. He observed that when the same current I was passed for the same time t through coils with different resistance, the heat produced was found to be proportional to the resistance of the coil. That is, H1 by R1 is equal to H2 by R2 and is equal to H3 by R3, or H is proportional to R. The same experiment was repeated by passing the same current through a coil of resistance R for various time intervals. He observed that H1 by T1 is equal to H2 by T2 and it's equal to H3 by T3, or H is proportional to T. These observations were mathematically summed up as H is equal to I squared RT, and this is the mathematical representation of Joule's law. An example: an iron box has a resistance coil of 30 ohms and takes a current of 10 amperes. Calculate the heat in kilojoules developed in 1 minute. In the solution, resistance R is equal to 30 ohms, current I is equal to 10 amperes, and T is equal to 60 seconds. H is equal to I squared RT, which is equal to 10 squared times 30 times 60, which is equal to 180,000 joules. This is equal to 180 kilojoules. Electrical energy and power. If you recall, in electricity, we said that potential difference is the work done in moving a unit charge from one point to another. We said that potential difference is given by work done in joules over the charge moved in coulombs. So V is equal to W over Q, which means that W is equal to QV. Again, in electrostatics, we said that current is charge per unit time. That is, I is equal to Q over T, which means that Q is equal to IT. Given that W is equal to QV and that Q is equal to IT, then W is equal to VIT. This is also an expression for work done. So the work done in pushing a charge around an electrical circuit is given by W is equal to VIT, so that W over T is equal to VI. But then work done over time taken is equal to power, and hence electrical power is given by P is equal to VI. From Ohm's law, V is equal to IR. Substituting equation 2 in 1, power is equal to I squared R. Also, I is equal to V over R from Ohm's law. Substituting equation 4 in 3, power is equal to V squared over R. In summary, electrical power consumed by an electric appliance is given by P is VI, or P is equal to I squared R, or P is equal to V squared over R. The unit for power is watt and is equal to the rate of change of energy of 1 joule per second. That is, 1 watt is equal to 1 joule per second. Therefore, an electrical lamp with a power rating of 1,000 watts converts 1,000 joules of electrical energy into heat and light every second. A larger unit of power is the kilowatt. 1 kilowatt is equal to 1,000 watts. Let's take an example. The potential difference across a lamp is 12 volts. How many joules of electrical energy are changed to heat and light when A. a charge of 5 coulombs passes through it, and B. a current of 2 amperes flows through the lamp for 10 seconds? In the solution, work done is equal to QV. Energy changed to heat and light, W, is equal to 5 times 12, which is equal to 60 joules. B. Work done is equal to VIT. Energy changed to heat and light is given by 12 times 2 times 10, which is equal to 240 joules. Applications. When current flows through a conductor, the conductor offers resistance to the flow of current. The work done in overcoming resistance appears as heat energy. Electric irons, kettles, cookers, ovens, and immersion heaters are appliances which make use of the heating effect of electric current. These appliances use nichrome as the heating element because it offers high resistance to the flow of current and has a high melting point. Electric iron. The primary requirement of an electric iron is the uniform distribution of heat over a large surface. A metal which is a good conductor of heat is used as a base. The metal plate is usually chromium plated to make it smooth and withstand wear and tear. The heating element is wound around a flat sheet of mica and sandwiched between 2 insulating sheets. Mica is chosen as insulating material because it is a bad conductor of electricity but a good conductor of heat. Moreover, it has a very high ignition temperature which prevents it from catching fire. To prevent the upward flow of heat, it is covered with asbestos on the upper side. As a result, all the heat produced is passed on to the base. Modern iron boxes have thermostats which cut off the current when the temperature of the base exceeds the chosen temperature. Some of the high-quality irons have a Teflon layer on the base. This prevents the clothes from sticking to the base and getting burnt. Some of these have facilities for storing water for spraying, either a nozzle to spray or an outlet from the base. The filament bulb. This is a common household light bulb. It's simple yet brilliant. It was invented in the 1800s and amazingly, it hardly changed a lot. It works by using a simple circuit and most important is the filament. It's at the center of the bulb mount and is made up of a long thin piece of tungsten metal which has an abnormally high melting temperature. Flow of current through the tungsten filament causes heating and the filament becomes red hot, giving out light. fluorescent lumps. These contain mercury vapor and inert gas. When current flows, the electrons hit the mercury atoms. Energy is transferred to the mercury electrons, pushing them into the higher orbits of the atoms. When these electrons flow back to the original orbits, they release this energy in the form of UV radiation. The UV is converted to visible light by phosphor coating on the inside of the glass bulb. It has a tungsten filament at either end. The idea is that heating it for a moment encourages electricity to start flowing. There is a starter to do this switching and a balance to limit the amount of current that can pass through it. Inside, the bulb is filled with argon and mercury vapor. This is mostly giving out UV radiation, but fortunately, there are chemicals that convert the UV into visible light and it produces fluorescence. If I switch off the light for a minute, you can see that they are all white powder. Manufacturers mix these fluorescent materials, creating combination of colors. These are coated in the inside of the tube. Fuses. A fuse is a thin metal wire that protects a device from much current. When electrons flow through a circuit, they create heat in the metal wires. The thinner the wire, the harder it is for the electrons to move, so more heat is generated. When there is too much current, the fuse acts like the weakest link in a chain by heating up more quickly than the other components, and it melts. That cuts the current flow and protects the expensive component from damage by heat or fire. If a motor draws too much current too quickly, the fuse will blow.
X-rays were discovered by Willem Conrad Röntgen. He had photographic plates which were kept in a light-tight container so that daylight could not get to these plates. These were kept in a drawer. For some reason, Röntgen actually decided to develop these plates after having played with his cathode ray tubes. Now, remembering the light from the tubes had no way of getting to the photographic plates. Yet, when he developed the plates, they were exposed. There were markings on the plates that shouldn't have been there. He had then discovered what we today call X-rays.